It's Rendon-Morales from Sussex University, UK. She's going to present something that I'm very excited about personally. It has to do with special sensors that were developed and patented at Sussex University already dated before me and Elizabeth started working on our research. So it's very exciting to see Elizabeth and team taking this forward towards monitoring. So I'm looking forward to that.
Thank you very much. Thank you. Good morning, everyone, and thank you very much for inviting me to do this presentation. As Antonia said, I work at the University of Sussex, and I am here to present a special type of sensor called electric potential sensor that has been designed to monitor the electrocardiogram activity in fetus and neonatus non-invasively. So I am going to share also a little bit on what is the actual development towards defining a smart wearable garment in order to monitor this fetal ECG at home. So then, first what I would like to start is, as I said, I come from the University of Sussex. My expertise is in sensors and electronics. And what I am trying to do is very similar to our two previous speakers, but in order to detect the ECG activity from fetus, but I am using, instead of all these amazing techniques that they have been describing, is using electronics, is use analog electronics, which is basically circuits that I designed so that we can remove all the noise and we can retrieve the electrical activity from the fetus non-invasively using this type of sensor, electronics. So, but first I need to show you this specimen. So this is, do you know what is this specimen? It is called zebrafish. Maybe you have it at your homes in a fish tank. So this is the initial research that I started. So when I started working in this area, I received the challenge to monitor the electrocardiogram activity of this specimen. This specimen is the size of 10 millimeters. So the heart is of the size of microns, 100 microns, as you can see. So for me it was a challenge because we need to develop electronics in a very reduced size, miniaturized level. But most importantly, it works underwater. So I need to develop electronics and sensor development that could work inside water, was the second requirement. And the third requirement is that this is very weak amplitude. Imagine a very tiny heart, how we can use electronics to retrieve the electrical activity and then to see if this fish is alive. Well, this specimen is mainly used for drug discovery applications. And mainly also for example, could be used for in vitro fertilization, because all these, the objective is that we can do different techniques. The doctors would like to do, biologists, so they would like to do different techniques on drug discovery on this specimen. Because one of the things is that the heart develops in just 24 hours, and for example, they could detect arrhythmia, QT prolongation, all this in this specimen that we can know, for example, do it in early pregnancy. So that's why this is interesting. So then I started my work, I started developing the sensor, and then we succeed developing some type of sensor called electric potential sensor, where we could sense the electrocardiogram activity of that specimen in vivo. So this was published in 2017. And this is more or less the ECG signal that we collect, which is on the order of microvolts. As we said, a lot of noise, so we need to use a lot of hardware techniques to reduce noise, and also signal processing techniques to use the noise. But then, after that, I met a group of people at the Brighton Hospital, and specifically a neonatologist called Dr. Heike Rabe, and she was very interested in my development. Because what she explained me, because I was not really very focused on fetus, so I was more on this biological specimen. But what she explained me is that this has a lot of relationship with fetus and also with premature babies. Because when the baby is inside the womb, we need to pass through the different layers in order to detect the cardiac activity, and we have the amniotic fluid, right? So and also we have the cardiac activity is very weak on amplitude. So all this, if we can use one sensor to measure that during the pregnancy, will be very, very useful for that. For that. So we started doing this work with the neonatologists at the hospital, and working in collaboration, trying for me as engineer to understand what are the real needs from you, because we talk different languages. That's why this kind of the talks are very good, because we need to understand each other so that we can develop more. And the most important to say with this is that the technology that we are developing at Sussex, we can made custom-made technology for a specific application. So how our sensor technology works. So this is a very basic diagram how this works. I am going to explain with very simple words, because Antonia also told me don't be technical. But the most important to say is that imagine that we have this road in this, which is imagine this is the heart activity, and this is a negatively charged rod. What I do is I design this kind of metal plate, and with this kind of metal plate, I charge my metal plate with positive charges, so that this electric field detection will come directly to my metal plane, and I use a capacitor, which is a passive element in electronics, to store all the charges of the electric field. And then in parallel, I use a multimeter so that we can retrieve this information. This sensor is non-invasive, could work underwater conditions, as I said before, because of the design of this plate, and then this is called electrometer-based amplifier sensor. And this is the principle what has been invented many years ago about a columbeter, which is a columbeter meter. So which is retrieving in a non-invasive way, like a small antenna, the electrical activity that is coming from the heart. So this is, for example, the zebrafish heart or the baby heart, right? So then we started designing electronics. I described my sensor very basic, but the truth is that it's not as simple as that, because we need to use amplification stages, a lot of feedback circuits, so that we can retrieve the information. This is the sensor from end. So and we use different type of materials, and we need to couple this either with the skin, with the water, depending on the condition of these specific cases that I am trying to test. So then I use electronics, so that then I use hardware low pass filter, also hardware notch filter, so that we can eliminate all the kind of noise, and then we enter into the analog to digital converter, so that we can use all the post-processing techniques that my previous previous speaker were talking about. So then with this, I can customize, as I said before, this from end, and then I can apply either for the zebrafish, for fetal, or also for neonatos. So what is important to say is that this sensor is high input impedance, which means that this is very important to make a very good couple with the skin, so that we can retrieve exactly the information from the heart, regardless the skin of the baby. So we have low input capacitance, which means that we don't drive any current, so our sensors are totally passive, in the sense that we just position the sensor in close to the heart, and then we are able to collect the ECG information. And then this produces a very low noise reference output in the sensor, which is very important for the type of applications that we're talking about, which is the fetal ECG, which is also affected by movement of the baby. So then I started this journey with the neonatologists at the Alexandra Children's Hospital in Brighton, and the first objective was to define this during pregnancy. So as you know, this is the type of technologies that when mothers go to the hospital, they need to be like this. And my sensors are very small size, and the most important, well, as you know, it's very important to have an effective method to ensure the well-being of the baby. And the most important for me was to work closely with clinicians, so that we can develop that technology together and help them to do informed decisions using this kind of technology. So for that, I need to understand more what is the medical need. So working in collaboration is very, very important. So, and as has been mentioned before, these kind of technologies could be very useful for these high-risk pregnancies that nowadays we are facing more frequently. So we have several current solutions in the market. So many people also from companies are here. We have the Philips technology, Pregnavit, Meridian, Monica, and here I have put this table describing a little bit what are the main characteristics on this kind of technologies. But the most important to say is that most of the technologies are clinic based, so we need to have these at hospital. So in case of any emergencies, mothers need to run and go directly to the hospital because they feel that the baby was not moving, and then this is an emergency. So for that also we need to have trained people. So clinicians should have training so that they learn how to use the devices. So this is one type of limitation if we would like, for example, to do home-based monitor. And another thing to say, this is was mentioned from previous speaker. Some of these technologies are complex because this is huge technologies that we cannot transport. So they need to use gel and skin preparation. And in case that the gel dries out, the signal is very difficult to pick up. And also another disadvantage or challenge of this kind of technology is that they need to use algorithms to separate mother and baby ECG. So based on this, what I also wanted to mention is that there is a global. Let me see if I can skip anything here. Okay, so there is a global market, well, based on fetal ECG. Nowadays, it's very important that we do more frequency monitors. And ideally will be that we can have a technology at home that a mother could wear and in the comfort of their homes, and they could be just constantly monitored. But the most important is also without generating any stress on them, because there are also fake technologies that promise to measure fetal ECG, and this is not true. That's why, China, for example, the Asian countries are highly growth markets, which means that many people here are highly demanding this kind of monitors, home care monitor, and the US is one of the leaders in this, trying to developing this or testing this kind of technology and making that there more portable, and the Europe, which is also part of this need that they would like to have compulsory, strongly recommended in many countries to perform fetal ECG testing in order to prevent for low risk pregnancy. Sorry. So fetal ECG at home base is an emerging technology. So and there are prominent companies working on that. So this is also very recently news, but in the UK, for example, there has been an investigation what are the main mistakes that have been done in the maternity wards related to the treatment, and most of these mistakes have been related to the treatment and procedures during the delivery of babies. So that's why the developing, again, the technology together with the clinicians so that we can identify more closely the need, and then we can provide better solutions is mandatory. And the testing different technologies, so as the speaker before said, that we can complement information. Not is competing against technologies, is trying to retrieve from ultrasounds, from CTGs, and from my sensor, which is my objective, that we can complement all this information and we can provide more robust diagnostic and give more certainty to mothers and babies, of course. So this is one of the news that was being released in the UK. So then this is my project. So we are with our three partners, which is Alexandra Children's Hospital and the Cranfield University, and our objective for this mother project, which is called Maternal Internet of Things Wearable Garment for the detection of fetal ECG. So one of our objectives, our objective is to develop this wearable garment that mothers could wear at the comfort of their home. This should be wireless, so that it needs to send information wireless, so this could be always and constantly monitored. And this will be used for high-risk pregnancies that require regular fetal ECG, and then and then what we use is a combination of printed electronics, apart from the sensor development that I said before, and then the objective is to embed our sensors development, our electric health potential sensor development into a garment and into cotton and several materials, so that we can wear and then transmit this information wireless. So this is an experimental setup that has been built in my lab. So what we do, we modify mannequins. So what I do is I change this mannequin internally to generate electrical activity and simulate our heart, mother and baby together. And then in this garment, this is where I embed my sensors. So I didn't put any scale, but the sensors are very small. And with this is what we call the front end of the sensor. And then we start testing and doing some analog electronics outside, and this is just some monitor, so that we can validate the feasibility of my sensor for this kind of applications. So then we did an initial trial using our electric potential sensing technology, and what we basically do is we develop a garment with just 4 sensors. 2 sensors here in the close to the heart of the mother, and 2 sensors in the maternal abdomen. Then we use the output, amplification, and filtering stages, and a graphical user interface. So we tested in a participant in a singleton pregnancy, and it was done at the University of Sussex in a calm atmosphere, so that she cannot experience any stress, and then we can be able to validate the principle of our technology. So the mother was laying down right and left lateral position, and the baby was, and then we identify the baby where was the baby, because then in order to monitor the activity with our sensor. So we did, the most important is that we make the volunteer to come during 10 weeks to monitor all the ECG activity during the 10 weeks period, starting from week 10 of the pregnancy, week 20, sorry, and finishing at week 30. So this is the ECG signal that we can retrieve from our sensor, from fetal and maternal. I put it here in the same graph, but the truth that they are separated, because one of the advantages of the sensors that I mentioned is that they are highly directional, which means that once we identify the position of the baby, we place the sensor close to the abdomen, and we can retrieve the information of the sensor of the baby non-invasive. So then this is the raw data that we get, and as you can see, is quite good to differentiate both, just doing very simple separation of the, not separation, very simple techniques for eliminating noise, we can retrieve both information. So this is doing a little bit of post-processing, week 20, how the ECG looks from the mother, which is the blue one, and the red one for the babies. And this is for week 25, and this is for week 30. And what you will, well, we didn't continue with the measurements, because at week 31, 32, we realized that our technology was not able to collect the ECG signal. And we were thinking, why this does not work? Well, we thought that this not work, but talking with our clinician partners, at around week 30, the Vernex gaseosa layer is created. And this layer totally protect the baby, so that as my sensor is based on electric field detection, so this layer protects the baby, so that's why this is not possible to get the information from the baby. But the most important to say is that the technology could provide us additional information because the baby is doing okay at week 30. This baby was born at week 38, and the most important to say is that for us, the most important was to test the principle. The technology is working. This is the first time this kind of recording at week 20 has been developing with a pure contact sensor, and then trying to track all these during the several weeks. So as I said before, this is the gestational week, so from 20 to 30, and this is the heartbeat information. Here the blue one is the mother ECG. So as you can see, it was pretty constant, so we try to keep her calm so that the baby start having this kind of behavior, very high beat per minute, and then approaching to birth, the baby start dropping down this heart rate, which is abnormal during the pregnancy. When the clinicians validate that this information, so this is the average information, and this has been published. And the most important to say here, we are now at the stage working on embedding our sensors on the textile, because as previous speaker also mentioned, one of the plans is that we can make an array of sensors so that we can monitor from several positions of the baby and test also on twins, which will provide us different information and complementary information that haven't been revealed before with this kind of technology. So then the other project that I wanted to share with you is part of this interest of continue working with clinicians on this neonatal technology development, is that once the baby is born, we are interested in measuring the heartbeat immediately after birth. Some of the people that I am working, for example, when a baby is immediately born, they do a technique which is called delayed cord clamping, that maybe you know, that maybe a clinician will know. That is, for example, delaying the time when we cut the umbilical cord. And this is very important for premature babies, because they then do this technique that is called milking, that they send some blood through the placenta, although the baby is outside. And this has proven to be very beneficial for babies, because if they are premature babies, we are talking 28 weeks of gestational, 28, 30 weeks of gestational. They are very weak babies, so this is very important. So that's why one of the main objectives of these technologies was to assist clinicians during the delivery of the babies. What happened with premature babies, for example, is that we have the cardiac, that baby, the cardiac activity is very weak. The baby, when it is outside the womb, is very wet. So we need to have technology that once we place the baby on the top of a technology, we can send that information. So for that, we developed what we call a wearable garment, a smart mattress for the detection of the cardiac activity of babies immediately after birth. So our objective is, when the baby is out of the womb, we put it on the mattress, and the mattress is embedded with an array of sensors, and this in order to sense the electrical activity from the back of the baby. This is very important, for example, for resuscitations, because what happens, babies are full of leads, so doctors cannot work on the heart. So if they don't have any leads here, they can push, they can do, they work, and they having a monitor that can provide So this is the NeoSense mattress. So we also tested on and this is more or less the mattress. The objective is that we place the baby immediately after the womb. So all the materials has been tested by biocompatibility. Our device works standalone, and so that once this is done, the clinician works on the work that is most important for them, which is saving the baby life. And we work in collaboration with this clinician, and we are performing qualitative studies, which some of you know, taking your views. What do you think about our technology? And then we modify it so that we can, so that we develop the technology that is going to be really used by people like you. So finally, this is the results. We collect from a young infant the ECG signal, the respiration, and was validated to measure the heart rate. And we compare that with the gold standard, which is the pulse oximeter. You may not well know that all babies are using pulse oximeter, but the technology is really not suitable for babies. Very weak, with a very heavy, with a small finger. So that's why having this kind of mattress would be beneficial for the babies. So this is the proof of concept study. In this, we are in starting clinical trials for the mattress so that we can test that at the hospital. And then to conclude, just wanted to show you a little bit of the work we have been doing, working more closely as from engineering side with doctors to understand your needs. And the most important to say is that we are trying to develop this kind of innovative sensors, novel sensors tailored for a specific application. So it's not a simple task, but we have tests that it works for during pregnancy, and it works during delivery. So our objective is to make these technologies available to the world. And just wanted to mention, this is the team that we are working, and it's very important. If you are clinicians, I would like to say that please have patience with engineers. We sometimes don't understand your needs, but we are trying to do our best to understand you. And in the other side is the same. If you are engineers, just keep working hard and try to understand the clinician, because all this is very difficult task, but I think the objective is the most important, to save the lives of babies, to help clinicians to do better their job, and to have real technology that people can use. The technologies in labs are nothing. We need to take that out and have it in the hospitals, and this is the objective of my research. Thank you.
Thank you very much, David. To remind you actually why I was here and what is the goal. And I think it was a lovely talk. We will have a few minutes. I know we are ready for coffee, but let's have a couple of questions.
Please. Thank you.
Thank you for your talk. It was very interesting. My name is Sarah. I come from Nettle Medical in Norway. Okay. Yeah. My question is, you said that you lose the signal at around week 32, so you can't use it for labor management.
This is, we are now, at the moment, no, because we need to modify the sensor front end, and we know that after week 38, the Vernix gaseosa is almost gone. So this is when we think we could test. But for that, we need to test with real participants and do more tests on the technology. The advantage is that I can modify the sensor. If once I collect the signal, I can do some electronics and modify and try to test it to see if this is going to work. But at least it's promising because it gives us information related to the creation of the layer, which is very important for babies. Yes, sorry for the late.
Very interesting. Did I get it right that you only tested it in one patient, one pregnant patient, and you stopped recording at 32 weeks? And I also understood that you don't need any skin preparation. So is it just contact? And do you get a good signal quality throughout the 10 weeks?
Absolutely.
All the time?
Yes. This is we have. Well, the one advantage is that we don't need to do any. This is raw data. We don't need to do too much cross-processing technique and high quality CGC.
But no signal loss at all with movement of the mother, movement of the baby.
And another, well, we did. That's why I said the first test was mother laying down in a calm atmosphere, so that we try to avoid moving artifacts, because, as you said, this is very, very challenging. But part of the test we are planning to do with the hospital is try to test the sensor with more participants in more real situations where we can have, for example, the movement of the baby, which could be also shown by the sensor.
So this was every day for a short time of monitoring. For how long were you monitoring?
The patient was with us around 1 hour every day. So we took around 60 minutes tracing monitoring on that.
Thank you.
Thank you very much. It's very early stage, I think.
Yes.
It's very, very promising because of the technology.
I will be around in the coffee. If you would like to talk to me, I would love to talk to you.
Tomorrow, right?
Yes, yes, I am.
Wednesday, conflict. So yes, so Elizabeth and Rodrigo is around as well.
No, I am.
Okay, so
Yes.
Elizabeth is
Elizabeth,
around.
I will be, please.
Very quick announcement. We've got now Wi-Fi and